As we saw in the previous part of the lesson, we have a ForkJoinPool class where you can submit tasks. You can submit runnables, you can submit callables, but most interestingly, you can submit ForkJoinTasks or instances of subclasses of ForkJoinTask. And so that's what we're going to talk about now, the ForkJoinTask, which is a common means of getting work to be done by the ForkJoinPool. So let's talk about the ForkJoinTask. The purpose of this task is to associate a chunk of data, which is usually a piece of the overall data set that you're working on in parallel, along with some computation that processes or modifies or does something to that data, or that chunk of data, that slice of data. This is used to enable fine-grained data parallelism. So you can have very fine-grained as opposed to coarse-grained. Remember the earlier versions of Java, like the Java Executive Framework, or I guess I should be more specific, things like the Java fixed-size thread pool in the Executive Framework, or the cache thread pool in the Executive Framework. Those had coarse-grained parallelism. This is for fine-grained parallelism. As we talked about earlier, and you'll hopefully remember the visual metaphor, the ForkJoinTask is like the scrawnier, but perhaps more nimble cousin or sibling or whatnot of the Java thread, which is much bigger because it's got its own runtime stack, it's got its own registers, it's got its own thread local storage, and so on and so forth. So because the ForkJoinTask is a little scrawnier but a lot more nimble, you can create a whole lot of them. You can have millions and millions and tens of millions and hundreds of millions of ForkJoinTasks without causing your program to come to a screeching halt or your computer to come to a screeching halt. And these run in a much smaller number of worker threads in a ForkJoinPool. So you can have a small number of worker threads, typically somewhere around the number of cores on the processor that the Java execution environment is aware of, and then you can have gobs and gobs of ForkJoinTasks that are running around. Once again, each worker thread, these are the things in the pool, has its own stack, its own registers, et cetera, and the ForkJoinTasks are then multiplexed on top of those. The ForkJoinTask class has two methods that are used by either you and or the framework to control parallel processing and merging. And those methods, surprise, surprise, are fork and join. And so we're going to look at a little diagram here to help make this more clear. So you can see there's some parent ForkJoinTask, which is going to go ahead and create child tasks, and it will then fork them. And when they're forked, they are given the opportunity to run in parallel. And then when they're done, the parent will join them and get the results back. So that's fork and join. So let's talk about fork first. Fork arranges to synchronously execute a task in the appropriate pool, which is either the common ForkJoinPool or a more specific ForkJoinPool that was created explicitly for this particular computation. And you can think of fork as being a lightweight variant of thread.start. So if you're familiar with Java threads, you want to start a thread, you say thread.start. That makes a new thread. We don't want to make a new thread because, at least in the traditional Java threads, thread.start creates a platform thread. That's way too heavy weight. We want a ForkJoinTask, so we fork it instead. Would probably come as no surprise that Java virtual threads, at least right now, use ForkJoinTasks to implement their lighter weight behavior. Fork doesn't actually run the task right away, but instead it places it on a work queue in the calling worker thread. So when you have a program that says fork, that thread that you forked in will go ahead and take the subtask that you created, which is this instance of ForkJoinTask, and it'll push it onto a work queue, which is actually a deck, a double-ended queue, in the context of the calling worker thread. We'll talk later about how it gets out of that thread's queue and perhaps on another thread that's a worker thread to do its processing in parallel later. Join returns the result of a child task to the parent task that forked it. So if you've forked something and then you want to get the results back later, you join with it to get the result of the computation when it is done. Unlike thread join, which is what you'd use if you were doing traditional Java barrier synchronization, ForkJoinTask's join method doesn't block the calling thread. Join on a thread will wait for that thread to finish. It'll block. But ForkJoinTask doesn't block. Instead, it uses the worker thread that called join to pitch in to run other tasks. And this is what I call the collaborative Jiffy Lube model of parallel processing. And the idea is if you've ever taken your car or your family's car or your sibling's car or whatever to a Jiffy Lube, you know it typically works like this. Jiffy Lube is a place you get your oil changed quickly. They'll typically have multiple bays. Let's say they have 4 bays. And you go in, you drive into the bay when it's your turn, and you queue up waiting to go into the bay if the place is crowded. And when it's your turn, you drive in, and then a mechanic or two will come and change your oil, check your tire pressure, check your windshield wiper fluid, offer to sell you new windshield wipers, offer to do this, offer to do that, a number of things that all happen. And the way this would work is if everybody's busy, then the worker or two that's working on your car will work on your car. However, if it turns out, for example, that a lot of the bays are empty, then when a car pulls in, the other people who would normally be assigned to their separate bay can then pitch in and come over, and they can all work on your car in parallel. So you get your car done faster. If there's people, if they're workers who have nothing else to do, if they're idle, they can come and pitch in and help out. So that's kind of the model that we see here when we do a join. When a worker thread encounters a join, it processes other tasks until it gets the result it was waiting for, and then it takes that and returns the result. There are a bunch of ways of being able to give non-ForkJoin task clients a means to get ForkJoin task instances processed in the ForkJoin pool. And those are execute, invoke, and submit. We're going to talk about all these things later when we talk about the details. Yes? Great question. So the question is, when we fork, are we always creating 2 things? Usually what happens in practice is the thread that wants to run something in parallel will fork a subchild on half of what it wants to be done. Let's say you have 100 items in your list. So when you first fork, the compute method will take the right half. It'll make a new ForkJoin task for the right half, and it'll hand that and say, fork yourself, and it'll go schedule itself and get ready to run. It will then process the left half. So it'll actually split it in half, and it'll process it. And that's because you don't necessarily want to create a task whose only purpose is to wait for its 2 children to finish. So usually a task will fork one task, give it the right side. It will then work on the left side in parallel. And we'll see some examples of that when we look at the code. That's a great question. There are variants of that, but that's a very common way to do it. What happens here when you call these methods like execute and invoke and submit is they take the object, the ForkJoin task, from a client, so this is the client over here, and they go ahead and put it in a shared queue, and that shared queue is then going to pull stuff out of, or sorry, the threads in the ForkJoinPool will pull things out of the shared queue and do their thing on them. So you can see this is a way of getting the work from non-ForkJoin clients into the ForkJoinPool, where things then work as they work in all cases. And there's a work stealing algorithm that we'll talk about in more detail, and that enables high core utilization. The goal is to keep all these cores hopping away, doing as much as they can. And again, think Jiffy Lube, multiple bays, multiple workers. Their goal is to keep everybody moving through that and giving you the best overall throughput and scalability possible given the amount of work to do and the amount of workers to do that work. So that's the end of the discussion of the Java ForkJoinTask class.